All right, well, I'll get started. I'm going to start by addressing, so you brought up you called it slip, slide, and divide. So let me talk about that. So this is a kind of a sneaky trick for dealing with factoring. So slide and divide. So what I'm going to do is I'm going to derive it. I'm going to show you why it's true. So we're going to start with f of x equal to something like ax squared plus bx plus c. All right. And then what we're going to do is we're going to take that and we're going to multiply by a times f of x. That gives us a squared x squared plus abx plus ac. And then here's where it gets sneaky. Sneaky step. Actually, the previous step was pretty sneaky as well, but sneaky step, y equals to ax. So if we let y equal to ax, then a times f of x is equal to, well, it's equal to y squared plus, notice we've got a and x, we got a b left over, so plus by plus ac. So that is the so-called slided polynomial. This is the slided f of x, right? But the truth of the matter is it's no longer a polynomial in x anymore. It's actually a polynomial in y. But if you can factor that, right? If you can factor that into, like, say, y minus r1 times y minus r2, well, then you're good to go. Because then what you can do is say, okay, well, if that's the case, then here's the punchline. F of x is equal to, let's say y minus r1 over a, sorry, not right yet here. So, y over a minus r1 over a times y minus r2. But in terms of x, what's y over a? See this up here? If y is equal to ax, then y over a is what? Just x again, right? So this is x minus r1 over a times ax minus r2. And that's the slide and divide method. Let me do it for an example. So if I had, like, example. So I'm going to discover y 3x plus 5 times x minus 2, which of course is what? 3x squared plus 5x minus 6x, which is minus x minus 10. I'm going to discover this factorization by the slide and divide. All right? So we start out with f of x equal to 3x squared minus x minus 10, right? Then if I was going to teach slide and divide, I would then say, so 3 times f of x is equal to, y squared minus y minus 30, where y equals to 3x. Oh, yeah, where y equals to 3x. And then this is equal to, well, that's y minus 6 times y plus 5 by ordinary garden variety easy factoring, right? Which is still guess and check. But of course, that is telling me f of x is equal to, and so then the trick is to put the 3 with the factor which has a 3 in it. You know what I mean? So in this case, I would do like y minus 6 over 3 times y plus 5. And that, of course, means 3x minus 6. No. 3x plus 5, which is, of course, x minus, yeah, you don't have to write it down if you don't want to. See, but if I was going to teach slide and divide, I would teach it this way, as to not offend my other sensibilities. Like, see, because the whole thing that offends me with the slide and divide is this doing, because I think students are going to write this, right? I mean, I know students. They're going to do this, right? They're going to say that this is equal, and then they're going to do x squared minus x minus 30, right? I mean, that's what students are going to write. But that's not what they mean, right? What they mean is you take this and you go to that, right? And then this is equal to x minus 6 times x plus 5, and so forth, But then you divide one of the factors by 3, right? Which one do you divide by 3? The first one, right? Yeah. The one that goes into, right? So if you understand that, you can use slide and divide for these problems if you want. It's fine with me. Just, that's all. But yeah, that's why it works. All right, now that I got that out of my system, let's move on, okay? So what is the method that I advocate in here for these kinds of factoring problems? What's the method? Right. So basically, my method is educated guessing, right? And I would point out that even the slide and divide needs educated guessing once you do the slided polynomial, right? It still gets back down to that. You notice that? Like, I still had to do educated guessing to get from here to here, right? That step is still educated guessing. It's just I'm suggesting if we have something like, 3x squared plus 4x, excuse me, let me put the number over here, plus 7. Oh, come on. All right. Yes?
Are you teaching?
I am teaching.
Sorry, can we close on Monday at 1?
Sure.
Okay, bye.
Okay, bye. Well, we will not be in class next Monday at 1, because I will be closing my house.
So no class?
I'll make a video.
Okay, so no coming in here, right?
I think so, yeah. I mean, tentative at the moment because, realtors and banks and stuff, let the dust settle, but most likely. Oh, you should be here for assessment day. It's very exciting. I heard that there's popcorn and pizza free, like free pizza, and they're gonna bring it. They're bringing in like a water slide. I heard there's gonna be like clowns, like face painting, and.
I don't like clowns, so.
I never made any claims about clowns in this class. You take that back. I'm the only clown. No, I is that right? Is the assessment day next Tuesday? That sounds about right.
Mm-hmm.
Yeah.
It's the 13th.
Okay, so I'm trying to come up with an example here. I'll say 20. I think 22 will work. I could be wrong. Let me think about that some more. Well, I reserve the right to change that 22, but so my method is kind of low tech. We just put down, if we have a 3, we try a 3x and an x to start with, and then we think about what are the how can we factor 7 into a product of whole numbers or their negatives, right? It's like, 7 times 1, right? Or minus 7 times minus 1. Them's kind of my choices. And so I need to put a 1 and a 7. So I need that 22, right? So that means I'm going to have to multiply the 7 by the 3 in order to get that big, right? So I got to put the 7 over here, almost have to. And that will give me 21. And then if I put the 1 over there, then I've got 1 plus 21, which is 22. So my method is simply write it down, put numbers in there, multiply, check that it works. Right? If it doesn't work, try a different combination. How many different combinations are possible? Well, that kind of depends on how interesting the number is that appears in the constant term, right? Here's another example. 3x squared minus 4x minus 7. So again, I'm going to put my 3x, I'm going to put my x, and I'm going to leave myself some space to try to write in some things. So the 7 is still, I either need a what to get a minus 7? I'll do the next part in red here. It's either like 7 times minus 1, right? Or minus 7 times 1. Which one am I going to want to go with? Negative 7. Negative 7. A negative 7 for the first one? And a plus 3? What? But I can't do plus 3. That would make if I put a 3, then I get a 21 for my constant term, right? I have to put a 7 and a minus 1 or a minus 7 and a 1 over here. Plus 1? Yeah, I mean, I could try the other way around, right? I could try a plus 7 here and a minus 1 over here, but when I do that, what happens? Then I get 7x minus 3x, which gives me 4x in the middle. But I've got a minus 4, so I have to put them in the other order. I have to do minus 7 and a plus 1 to get back to that. Do not panic. You can do these. You just need, after you make your choice, multiply it out, check your work. You will have time to check your work, right? And of course, if you're confident about your slide and divide, you can do that, And if you want to be taught slide and divide by a person who is less against it, you can ask Brianna. Or you can also ask the tutors in the other room, because one of the other professors teaches slide and divide. Like I think Professor Giles, like that's what she does in her class. So the tutors know to ask which class they're in, and different teachers want it done a different way. I'm open to either. You can, as long as you can find the answer confidently and correctly, I'm fine with it. Right? So if you want to be taught the slide and divide method, not by me, by someone who believes in it, ask the tutors next door. They can teach you as well. Yeah, or Brianna. But Brianna might charge. I don't know. Okay, so let's do some more factoring. Let's see here. How about x squared minus 5x plus 6? Or x squared plus 4x plus 8? Or x squared plus 16x plus 2? So what do I do? Three and 2, I like it. So this is either 3 times 2 or minus 3 times minus 2, right? So what'd you say?
X minus 3, X minus 2.
Minus 3. It's, we need the minuses because we got the minus 5x in the middle, right? Well, that's good. I just made this problem up. I wasn't entirely sure it was going to factor, so we got lucky. That's good. Wonder how long we'll get lucky in here. The next one also, it works? Now 8. 8 we could write as 1 times 8. We could write it as minus 1 times minus 8. We could write it as 2 times 4, right? Looks like we won't need minuses here, right? If it's all plus, you don't have to think about minus, right? So this is 1 times 8 or 2 times 4. Them's your choices pretty much. How about this? If we do x plus 1, we do x plus 8. Well, that's, let me put a question mark over that equals because I don't think it's true, right? I don't think it's true. What happens if we multiply this out? What do we get? We get x squared plus 1 plus 8. We get 9x, right? Well, that doesn't work, right? And what if we try the other one? Yeah. Yeah, we get x squared plus 6x plus 8, right? That don't work either. So what do we do with this? Put a what? Put an x over it and move on. Well, I'm going to, at the moment, say, so I'll just leave 3 question marks there for the moment. What are we going to do with that? See, that's a polynomial where our guessing and checking just doesn't work, right? Whole numbers aren't going to do it for us. How about this one? Two, it's either 2 times 1 or that's it, right? It's positive. So the only thing we could really try here would be plus 1 plus 2, And that's what? X squared plus 3x plus 2, right? So again, it's not working, right?
But there's one left down on the test.
What will we put?
So, and then a couple question marks.
So question mark, yeah. So there's another way, right? So, well, here's the thing. It could be that the problem is that we need to use more than just like, what's that called? It could be that we need fractions. That's one possibility. So let's start there. Let's look at an example like that. So if I had something like 2x minus 1 times 3x minus 1, that would give me 6x squared, excuse me, minus 5x plus 1. So this is, I multiplied it out, but my point to you is this is an example of factoring where this slide and divide wouldn't work here, for example, because there's a factor on both of them. I think that with slide and divide would get in trouble. Unless there's like a modified slide and divide, I don't know. So let's say, here's my example, x squared minus 5/6 x plus 1/6. How are we gonna factor that? You guys are like, "Whoa, no, what are you doing? No fractions? Life was so much simpler before we brought fractions into play." But if you had fractions, what could you think about? Can you write the fraction as a product of fractions, right? So this would be like what? Mm-hmm.
Why do we need, no, never mind, you want to make our way.
You talking about this one, or this one I didn't really factor. I just multiplied to show you that there are other things that could happen, right? Like if I started with 6x squared minus 5x plus 1, I would need to put a 2 here and a 3 here to get it. You know, it's not always possible to lump all the, I don't know what you want to call it, whatever you want to call the threeness of this 3 problem. You know, it's not always possible to lump all of that into one of the products. I did an example last class with like square root of 2 going on both. It was a similar kind of thing. What I'm trying to introduce you guys to the idea is, it is special and wonderful and in a happy place when the method we're doing works, when whole numbers allow us to factor the polynomials like we have been. And yes, certainly, you'll be asked questions like that on the next test, right? But I want to explain to you why we need to think about other possibilities. Partly because this is annoying, right? This is 1/2 times 1/3, isn't it? Golly. If I put a fraction on the test, you're just going to leave it blank? Let's see here. So plus, you guys are cracking me up. Minus 1/2, minus 1/3 is what I would try. Because, you know, I need the positive, but I got a negative over here. When you do that, what do you get? The right answer? Well, I hope so, but I don't know. I mean, this is x squared. And then we get, what, minus 1/2 plus 1/3, parentheses x, plus 1/6. See, because I get a minus 1/2 and minus 1/3. What's 1/2 plus 1/3? How would you add 1/2 and 1/3? Make a common denominator, right? What's the common denominator for 1/2 and 1/3? 6. So 1/2 is what, 3/6? 1/3 is 2/6. 3 plus 2? 5. So looks like Brianna was right. So it looks like it works, right? Now, this is, I mean, there are theorems that allow you to factor using rational numbers like this. There's something called the rational roots theorem that actually lays out like a precise and systematic algorithm, but I'm not going to teach that. What I'm going to instead teach you is a method which will always work, all right? Now, this method may or may not need fractions, but it doesn't require, like this requires kind of like pretty sneaky thinking about fractions, right? You got to think about how to factor a fraction into a product of fractions. Then you got to add fractions with unlike denominators. Like, that's a pain. What I'm about to show you is a cut and dried algorithm. It goes step by step by step by step. It will allow you to factor every single possible problem if it can be factored. If it cannot be factored, if it's actually what's called a prime polynomial, we will discover it in the course of this algorithm. So I think, you know, as I think about solving problems in here, here would be my attack plan if I was you guys. Here's the attack plan. So given f of x equals to ax squared plus bx plus c, and you know, you're asked factor over the real numbers if possible. Then here's what I would do. Number one, I would try the thing we've been doing. All right? I would try to use the guess and check whole number or the slide and divide method if appropriate, right? So number one is, try educated guessing. Educated guessing based, factoring. Right? On the other hand, if that doesn't work, then I would say use algorithm, which I'm about to show you. All right? The algorithm. So what I'm trying to say is, when we look at, let me number these examples that we've had so far today. 1, 2, 3, 4, 5. All right? So I would say for example number 1, we tried educated guessing. It worked. Game over. Right? Fine. Wonderful. Problem number 2, we tried educated guessing, and it didn't work. We need something else. Right? Problem number 3, we tried educated guessing. It didn't work. We need some other method to attack this problem. All right? And to decide whether or not, basically, whether or not it's something that cannot be factored over the reals, or if it's just something that's annoying, that has like fractions that are things we can't guess. All right? Because these examples 4 and 5 show you that, there are problems where we can't nicely factor using the whole number method, guessing method, and yet they still can be factored. It's just that they involve pesky fractions. All right? Okay, so here's the method. Algorithm. Step number 1. Given f of x equal to ax squared plus bx plus c, factor out a if needed. All right, so like the first thing I'm going to do is basically rewrite it as f of x equals to a times parentheses x squared plus b over 2a x plus c over a. So that's my first step. My first step is to just divide a out. All right? Step number 1, pull a out if necessary. Step number 2, all right? And this is where it gets weird. I mean, that step makes, oh, thanks. That step the first step is like kind of innocuous, right? Because we'd like to work with problems with an x squared rather than a constant. But the next step up is to rewrite f of x by taking 1/2 of the coefficient of x and writing a square. So in particular, for an arbitrary one, it looks like this. F of x equals to a, that a is still out front. We have x squared, rather we have, x plus b. Did I have a, where did this 2 come from? Come on, guys. Don't let me get away with that. This 2, bunch of nonsense. Where does 2 come from? What's that? I just made it up, right? I mean, that is not there. You factor out an a, it should just be a, right? You can't believe me? Now I'll put the 2 over here, though. All right, you're like, hey, wait, yes, but this is different. And so I'm going to square that. When I do that, notice that because x plus b over 2a squared is what? X squared plus b over 2ax plus b over 2ax plus b squared, b over 2a quantity squared. The point is that it gives us the x squared plus b, x squared plus b over a. So let me try to emphasize, let me try to explain what's going on here. In my previous step, I had these terms, x squared plus bx over a, right? What I'm trying to do is I'm trying to take all of these and put them together in one term that has a square and an x. So if I take x plus b over 2a and I square that, right? Look at what happens. We get x squared plus b over ax. That's the term I already had, right? Right there. So I can trade this for that. But when I do that, I've added that. See, this wasn't there before. If I write this, it's effectively adding this much. So we can't just add things to an equation, right? We have to subtract them if they weren't there to start with. So we subtract b over 2a squared. And then what else is there? Oh, that was my imagination. That was the sneaky step. The reason I put a 2 over 8, the reason I divided by 2 is because I know when I square this out, I'm going to recover this x term and that x term. So I'm taking the 2 x terms and I'm grouping them together as a single squared term. That's the idea. Right? I'm pulling the x's together into a single x plus something that's squared. This right here. But you see, I still got the c over a. Right? And so 3, let me just clean things up. This is the conclusion. F of x is equal to a times parentheses x plus b over 2a quantity squared. And then, so I can make a common denominator here. What's b squared over 2a squared? B over 2a squared is what? That's b squared over 4a squared. So, well, anyway, I could, let me rewrite that as, how could I guess I want to give them both a common denominator of 2a squared, right? So if I do that, I could write that as 2a, and upstairs I've got b squared minus 4ac squared, like that. Brianna's like, I knew what you're doing. I don't like it.
As soon as I heard you said 4AC, I was like, no, this part. Why don't we just do it?
So,
Over it.
please do not walk out. Listen, I will be doing this algorithm like 4 or 5 times with examples once we get through this. I need to show you the general pattern. Just bear with me for a minute here. So then the point is, this is a difference of squares, right? Notice that? This is a difference of squares. So as long as, well, that's the thing, is, excuse me, I did something wrong here. That's b squared minus 4ac over 2a squared. So if I can rewrite this, this is a times x plus b over 2a minus the square root of b squared minus 4ac over 2a times x plus b over 2a plus the square root of b squared minus 4ac over 2a, like that. Now, when does that step work? What do we need for that last step to make sense? I think the square root of b squared minus 4ac, right? For that to be real, what do we need about b squared minus 4ac? We need b squared minus 4ac to be greater than or equal to 0 for my last algebra step to make sense with real numbers. So what I'm telling you is we can decide whether or not a given quadratic can be factored nicely or possibly ugly with real numbers by just checking if this quantity b squared minus 4ac is non-negative. That will decide for us whether or not it's possible to factor or not. This is called the discriminant, because it discriminates what kind of problem you have. Now, so let me actually go through that algorithm here for a bunch of examples. Isn't it what? It is very close to the quadratic formula, yeah. But I haven't solved the quadratic equation, you know. So here, let's consider this x squared plus 6x minus 10. So if we follow the attack plan, the first thing we would try would be what? Plain old garden variety factoring. What happens if we try that? I'll just tell you what happens. It doesn't go well because you've got 2 and a 5. So you can either get 2 plus 5, which is 7, or you can get like, or excuse me, it's a minus, right? So we can either get 5 minus 2, which is 3, or we can get 2 minus 5, which is minus 3. If we do 1 and 10, we can either get like a 9 or a minus 9, depending on whether we do 10 minus 1 or 1 minus 10. So if you think about the numerics of like this minus 10, you see either of the factorizations of 10 is 1 and 10 or 2 and 5. They don't produce this 6, right? So we could try our easy method. It doesn't go well. So we'll try the other thing. And by the way, this algorithm has a name. It's called completing the square. I was not saying it at the start in the hopes that Brianna would not give up on me immediately, but I think please do not give up on this before you guys start. Do not do that. Everyone can do this. It's not the end of the world. It really isn't. So we take, first of all, tell you what, I'll make it easier. I will not ask you a completing the square problem where a is equal to anything except for 1. You have my guarantee. I will assume a is equal to 1 in this class. If I ask you a question that involves completing the square, I will make a equal to 1. All right? Then all of a sudden this gets much easier. So let's do it. So if a is equal to 1, then all we do is we take step number 1. You take half of x coefficient, right? So here, we take 6 and divide it by 2, you get 3. So we take x plus 3, we group them together, we square them. Now think about this. What's that? How we get 10, right? How do we get... First of all, what happens when I do that? Like, what does that do to us? Like, what is x plus 3 squared, by the way? Well, x plus, yeah, what, multiply this out, what do you get?
X squared plus 6x plus 9.
Right. So was that there to start with? No, it was not. So to be fair, when I write x plus 3 squared, I have to subtract 9. What I've written is exactly the same as the first two terms. Like, this matches that identically. And I still have the minus 10. Still have the minus 10, so that's there. And so what that's going to give me is x plus 3 squared minus, well, 19. So when we complete the square, and at this point the square is completed. That's what's called completing the square. Just that adding and subtracting, the grouping things together as a square and the subtracting the appropriate number, that's called completing the square. That's all there is to it. That's it. We're not done yet. We're going to use this now to factor. The thing is, when we complete the square, we'll have x plus something squared with a number, either added or subtracted, all right? If the number is subtracted, then we can look at this. We got to, just use your imagination, and you can see that this is what? This is x plus 3 squared. Well, no imagination yet, but this is minus the square root of 19 squared. So this is really the difference of squares. So what was our... That's one of our special forms, right? If we have something like a squared minus b squared, we go a minus b, a plus b, right? So I just need to think about, can I erase my step 2? It's kind of in the way. Poor planning on my part. Sorry about that. So I'm thinking of a equal to x plus 2, right? I'm thinking of b as being the square root of 19. So I get, x plus, did I say x plus 2? It's x plus 3. I'm a moron. So x plus 3 minus the square root of 19. X plus 3 plus the square root of 19. That is how this polynomial factors over the reals. That's it. That's the answer right there. I mean, that's the answer to, this is, Say again? Yeah. Well, that's how it's going to work out, yeah. But the 3 is the same for both, right? The thing is, you can still do this when it factors nicely. It'll still work for you. This always works, actually. You can modify your attack plan to just always complete the square, and it wouldn't be wrong, because you can always complete the square. But the question is, when you complete the square, there are 3 different things that can happen, right? So here's the 3 things that can happen. The one is you get x plus some number minus a number squared. The other thing is you could get x plus a number squared. The third thing, you could just get x plus the number squared. These are the 3 patterns, basically. I'm using Here, alpha and beta are just like symbols to indicate a number, okay? That's basically the three patterns. You either have minus a number, plus a number, or no number after you complete the square. So the first and the last case, they factor completely over the reals. In the middle case, that's when it's prime. That's when we cannot factor. So, and in fact, moreover, this is when b squared minus 4ac is greater than 0. This is when b squared minus 4ac is less than 0. And this is when b squared minus 4ac is equal to 0. Those are the three cases. Yep.
Can you explain one more time where the 9 came from in the first step?
Where the 9?
The minus 9?
Right. So we take half of the x coefficient, then subtract the square of 3 to be fair. That's what's underlined in the blue up there. We have to subtract the square of it because the thing I erased here, right, was when we multiply it out, we're effectively adding the square of, in this case, 3. That's all. Look, I could talk more about it, but it's probably better for us to do another example. X squared minus 8x plus 6. All right, so we take half of that, which is what? 4. But it's got a minus, so we keep the minus. 8 minus 4, quantity squared. The thing is, by doing that, writing this term, what have we effectively done? We've just added 16. So to be fair, I must subtract 16. So just to emphasize again, the first two terms here, if you multiply x minus 4 squared out and subtract 16, you get exactly back these two terms right here. And that 6 just rides along. What do we get? We get x minus 4 squared. What? Minus 10? What's that? Yeah, minus 10. So it looks like we're again in the first case, the positive discriminant case. Yeah, we think about this as, kind of use your imagination, right? This is x minus 4 squared minus square root of 10 squared. So difference of squares. So this is x minus 4 minus the square root of 10. X minus 4 plus the square root of 10. And that's factored completely. That's as far as we can go. With this simple trick, we can always convert every problem into a difference of squares. That's the idea. Mm-hmm. Mm-hmm. Now, I haven't solved the equation yet, right? Like, I'm just factoring. But we can, let's ask that question. What if we were to solve problems, right? What if we were to solve, here's the related question. How do we solve how do we solve the quadratic equation? So, solve this one, x squared plus 6x minus 10. You see, if we factored it like this, then it's a piece of cake, right? I mean, if you've got factors, what does this tell us? That tells us either x plus 3 minus root 19 is equal to 0, or x plus 3 plus root 19 is equal to 0. If I have this times that is equal to 0, then either one or the other is 0. If this is equal to 0, it gives me what? Minus 3 plus root 19. This gives me x equals to minus 3 minus root 19. And there you go. Those are the solutions. This one, if I was to look at x squared minus 8x plus 6 equal to 0, right? I could look at that right there, and I could tell you, okay, so x is equal to 4 plus or minus the square root of 10. In other words, 4 plus root 10 or 4 minus root 10. The reason that this is plus 4, whereas that was minus 3, notice that there's a minus 4 appearing here, which when we set that equal to 0, we bring 4 to the other, minus 4 to the other side, we get 4, right? This one, when we set that equal to 0, we get minus 3 because we have to bring the 3 to the other side to get a minus. So if you can factor completely, you can solve. But also, I mean, I would be negligent in my duties here if I didn't mention to you, if we look at my general algorithm, right, that we did at the start earlier in class, and you just ask the question, okay, f of x equals to 0, what is x equal to? What do you get from this step 3, you know? So I would say remark from step 3 earlier, f of x equals to 0 gives x equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. This, of course, is the quadratic formula, which is going to give you a real answer provided that the input to the square root, which is called the discriminant, is non-negative. You have some kind of traumatic experience with the quadratic formula.
I had a teacher in my 10th grade year that for a solid 3 months, all we did was quadratic formula, and she would find ways to put the quadratic formula into everything. So I have PTSD.
Post-traumatic stress disorder from the quadratic. You notice that I didn't even use the quadratic formula to find the answers here, though, did I?
I like that better. I like the way you did it.
What I'm saying is that when you understand completing the square properly, you don't need the quadratic formula anymore. You have become the formula.
I ain't becoming the formula.
You don't want. You think I don't want it. Don't put that on me. I don't want to be that. All right, fine. Let's look at another example. Let's say we had x squared well, how about x squared plus 1? This is kind of a stupid example. It made you go cross-eyed. Your eyes just went like, that was a high quality, like, that was a good face. Okay. If I could have that for a thumbnail, it'd been perfect. Yeah, what?
Is it x plus 1 squared?
Nope. What you're thinking of, Brianna, is this one. So let me point out this one. Let's look at things here. So here, if we compare this to ax squared plus bx plus c, right? Notice what we got here. We've got a equals to 1. We've got b equals to 1. Wait a minute. Do we have b equals to 1? B equals to what? I got a 0, right. C equals 2, 1. So b squared minus 4ac, the discriminant is what? 0 squared minus 4 times 1 times 1. It's equal to minus 4. So this is less than 0. This says that x squared plus 1 is prime. Or you could say it's irreducible. I like the word irreducible. It gets across the idea that you cannot reduce it. You cannot factor x squared plus 1 over the real numbers. That's it. Game over. There's no, what happens with completing the square on x squared plus 1? Notice that there's no b term, right? So like it's already completed. The square is already completed for x squared plus 1, and it's kind of stupid. You know? In contrast, how about the second one there? What happens when we complete the square here? But before I do that, any questions about that first example? So to me, x squared plus 1 is sort of like the quintessential, it's my standard go-to example of something that I cannot factor over the reals. If I wanted to think in my mind's eye, like, what's my standard example of something that cannot be factored? I think x squared plus 1. I know that one I cannot break it down. And so what I'm trying to say is if completing the square makes something look like x squared plus 1, then you know it can't be broken down. That's what case 2 is. This looks like x squared plus 1. It's the sum of two squares. That's what I mean by that. Anyway, this one, what do we got? X plus 1 squared, right? And then what we subtract 1, right? Because we're supposed to subtract the square of what we're adding, which in this case is 1. 1 minus 1? 0. Hey, wait a minute. And so this is what you should have noticed anyway, right? X plus 1 times x plus 1. That's how you factor this, right? We would get that from guessing and checking. But we just derived it from completing the square. Okay, so yeah, there it is. What if you set this equal to 0? What would happen? What are the solutions to the corresponding equation? I'll put it in red. By the way, x squared plus 2x plus 1 equals to 0 is really x plus 1 squared equal to 0, right? So that tells me that x plus 1 has to be equal to 0, which tells me that x equals to minus 1. That is my one and only solution here. So what you should be starting to see here is when we have a quadratic equation, we're either going to get two solutions, like we did in my first two kind of ugly examples, which involve square roots, right? The plus and minus, what are they different? Or we can get just one solution, like here, right? Well, how about what if I asked the question for this one, for a prime polynomial? What if I asked you the question, solve x squared plus 1 equal to 0? What's the solution to that? Can you solve that? That would be x squared equals to minus 1, right? Can you find a real number whose square is negative? You cannot, right? So in other words, there are no solutions to this one. There's no real solutions. No real solution.